Welcome everybody to the video presentation for the senior design project Bring Knightro to Life. My name is Taylor Bean and I'm acting as the project manager.
My name is Richard Penrose. I served as the Arduino and Servo Specialist.
My name is Samuel Bracena. I served as the artificial intelligence specialist.
I'm Gabriel Castaneda, and I was the audio and speech specialist.
And I'm Sarah Pagano. I acted as our natural language processing specialist.
So for the background of Knightro, he was a former senior design project from MAE, and his purpose was to try and inspire new students to join the STEM fields. And this is the general diagram that they used to design Knightro.
So for what we needed to change, first and foremost, our sponsor asked us to make Knightro smarter and more extensible for future developers. So to accomplish this, we need to change uh, pretty much the entire virtual assistant software suite that the previous team used to handle their student interaction, which was a open source software suite called Mycroft, which had a few problems. First and foremost was the extremely slow cloud-based intent handling system, which would require internet access for every intent. The second issue was an issue with created custom skills. As you can see on the right-hand side, each new skill, Mycroft required the users to add in a whole new repository, and this would have problems with code continuity and extensibility. Uh, the last problem we have with Mycroft was their poorly performing wake word engine that, according to the previous team, had a 25% responsiveness to their wake word, which was "Hey Nitro."
On the movement side of things, the initial movement interface had all motion controlled through a collection of keywords which together composed a giant switch case statement stored on the Arduino. This led to large Arduino file size with a relatively small number of movement patterns, but most importantly, it gave us no real control from the Raspberry Pi over the individual servos on Nitro's body. Therefore, in our version of the movement interface, we want to abstract the Arduinos away from the average developer and create them to see them more as motor controllers instead of microprocessors. And that way, they can be set and forget and act simply as relays for the Raspberry Pi's commands. Our approach for the movement interface we dubbed Pi to Eno, and as we alluded to before, it's simply just a conductor relay relationship. The Raspberry Pi is what determines and issues the movement command, and the Arduinos receive this information and just move the servo to the correct position. A movement sequence here is defined as a list of movement commands, and we created the movement controller, which acts as a builder to build movement sequences through a collection of movement primitives that we defined ourselves. And lastly, we use the packet serial communicator, which serves to use the serial communication between the Arduino and the Raspberry Pi, and all serial communication expects an acknowledgement, so it is closed loop.
So the Human to Nitro subteam dealt with the student interaction. Our plan or approach to this was creating a 5 artificial model intelligence approach to improve performance with student interaction, and basically essentially creating a voice assistant software suite from the ground up. So the 5 models include our wake word detection engine to detect our wake word phrase "Hey Nitro." The second one was the denoiser model to reduce noise signals for the speech to text model. The speech to text model, which would then transcribe what the user says after they said the wake word, which was "Hey Nitro." The text to intent model, which attempts to understand what the user wants. And finally, the text to speech model, where once the response is chosen, it speaks the response to the user. All these models work in tandem and will have to work faster with greater accuracy than the previous Nitro's implementation for Mycroft. Lastly, along with a verbal response spoken to the user, we can create a new motion using the list of primitive motions created by the Pydoino subteam.
So as for difficulties on the Pi to Eno side, we were trying to use an external library called the packet serial library. Essentially how this worked is that it took an array of bytes and it tried to send it over to something as a serial communication method. Unfortunately, it caused undetermined movement where the motor would go to the position the first time, but then it slams back to home, violating the safety principles that we were hoping to maintain with Knightro. So we had to replace the packet sender with our own packet structure. We also had a limited knowledge of hardware going into this project. I didn't know what an Arduino even was before starting this project. There was also some physical repairs we needed to perform on Knightro during STEM day. On the transition to the building, his head kind of fell off, so we had to reattach the head. And additionally, we also had to figure out the voltage for the power supply unit. Turns out that if somebody's fiddling with the knob while it's off, that does change the voltage. So we had to quickly figure out what that voltage was again.
On the human to Knightro side of things, some of the limitations we had were with the Raspberry Pi, where it runs on an ARM architecture. So unlike x86 and x64, it's not as easy to find compatible packages for it. Also, the Raspberry Pi has some weak hardware, so we had issues optimizing it to be an acceptable time for the user. And we also had some issues with the Linux operating system itself, because in the way that it interfaces with the Arduino is problematic, so we had to make special rules in Linux to account for that. There was also not enough training data for the wake word and intent classification models, so we ended up having to make a lot of our own data and augment it for the models to be trained efficiently.
So as for successes, as I mentioned before, we had an issue with the packet serial library that we were trying to use, so we constructed our own packet structure that sent over the motor ID, the angle we want, and the delay, which is the speed of how fast the motor needs to move. So the interface now sends our required information, and because of this, we were able to establish our movement library and even expand upon it, and probably most impressively, develop a multi-threading single-target broadcast over the mass broadcast it was using before, where it tried to send the information to all Arduinos. We now have a singular thread focusing on a singular Arduino each.
As for the human to Knightro side, the linked machine learning models perform very well for running on a Raspberry Pi, achieving times of as low as 2.5 seconds when responding to a user's input. The intent classification model performs great on our intents with a high accuracy percentage, so it's very good at knowing what the user wants out of Knightro. On top of that, it's also a simple process to add new intents. All that is required is some input text data as training, and as it needs to be retrained once, and then it's just drag and drop back into Knightro.
So, as we worked through this project, we came up with some future improvements. We won't discuss them all, as we discussed some, like we would like to upgrade from a Raspberry Pi to something more powerful. We also discussed maybe having some computer vision in the future to have Knightro follow an active speaker. But lastly, and most importantly, for Knightro to be fully alive and for him to fulfill his potential, we suggested that this would be a multidisciplinary project in the future, having both MAE and computer science teams working together.
And here's our demo.
Hey, Knightro. Hello.
It's nice to meet you.
Hey, Knightro. Tell me the weather.
This afternoon mostly cloudy, tonight mostly cloudy.
Hey, Knightro. What was the score?
In the most recent game, we scored 38 while Tulane scored 31.
Hey, Knightro. Show me a dance.
I've got the smooth moves.